we requested that the course be held online, and GIAN office must have received several such requests, and therefore they have permitted us to run the program online. So it is a matter of pleasure for us that all of you have joined. We welcome you on this GIAN course. I'm sure that you're going to have a wonderful experience. Today's program, today's sessions are mostly preparatory sessions. And for the first session, Professor Vijay Gupta, who is the coordinator of the program with me, has very kindly given his consent to deliver an introductory session on robotics, introduction to robotics. These sessions are planned just to give you a flavor of what is happening in robotics, starting from the fundamentals to the recent trends. And Professor Vijay Gupta has been working on robotics for a long time. And I'm fortunate that he keeps involving me in some activities. So I also work with him. Professor Gupta is professor in charge academics at the institute. He is a professor of mechanical engineering. He has expertise in various domains, including smart structures, smart and robotics and automation, soft computing, and whatnot. He graduated as a PhD from IIT Bombay long back, and then he served for a couple of years in Kota at Government Engineering College, and then he shifted to IIT DM Jabalpur long back, I think 2008, if I'm wrong, Professor Gupta. You're not audible.
2003, I had done my PhD, and then 2007 I joined this institute.
2007 he joined IIT Jabalpur. This was I was asking, and then ever since he joined, we have been working together on various different projects. I am sure that you are going to have a good experience listening to him. With this, I request Professor Gupta to please start his lecture. And may I also request you to please give me the YouTube link so that I can share with GIAN office. Thank you.
I had shared it on the email, madam, morning itself.
YouTube link?
Yeah.
Okay. So, fine. Because...
actually, it is on my YouTube, basically. So there it will be directly coming.
Sure, sure. Thank you. Thank you.
Okay. Thank you, madam. So, good afternoon, participants. So, we are starting this course. Basically, I am trying to just revise the robotics fundamental. Some of you might already be aware about this. So, what I have done is I focused towards the manipulator and mobile robot direction, because the rehabilitation and assistive robotics, that will be covered by the Professor Domenico. So my today's talk will be just to introduce you with the robotics, and then what are the domains in which we can work. So I'm just sharing the slides just a minute. And if you have any questions, you can interrupt in between. There is no problem. So are you able to see the slides?
Yes, sir.
Okay. Yeah, so the first talk today is the introduction to robotics, basically, and you can see here some of the work our master's students in mechatronics lab they've done. I tried to summarize them basically. So this one is the manipulator developed. This is a wheel mobile robot. These two are the assistive robots basically. So the work is going in this direction. So some of the aspects I will be covering in this today's session. So I start with the definition, basically what is a robot? What can be considered as a robot? We say that it is a autonomous thing. Someone says that it is a device which is powered by the motors, right? And similarly, it is having some computation work. So in this slide, there are different objects are shown. So for example, if you see this microwave is there. So if we set up the temperature and then automatically it will be working, maybe it is running for the 20 minutes or 10 minutes or 5 minutes. So it is doing its job autonomously, basically. The only thing we have to do is that we have to keep the food, set the timing, and then it performs the job. This is a car. Basically, this car, maybe nowadays the cars are also becoming autonomous. So we say that it is a autonomous running car. So can we classify it as the robot? Or if it is not classified as the robot, what is the difference between a robot and this autonomous car? Because it is fully automatically, it is taking its own decisions and then moving, basically. Right? Similarly, some other objects, this is a wheel device which is moving, and then you might have seen the humanoid type of robots which is playing some music. So what is a robot? Basically, according to Robotics Association of America, robot was first defined in terms of the industrial manipulator. A robot, basically the industrial robot, is a reprogrammable multifunctional manipulator. So this definition, it is having the focus on the manipulator. But if we see in the today's world, robotics world, the manipulator is a very small part, and the various other directions the robots have been developed. But still the definition may be extended to the other robots. So if we see that this robot, it is a reprogrammable. So we need that the robot should be able to perform the different tasks. We should be able to reprogram it. Maybe I have an arm which is working. For example, I've shown you this arm. So this arm, I may be using it for the pick and place. I pick something and I place it other place. It can be used for writing on the board. It can also be used for the welding purpose. It can be used for the painting purpose, and many other tasks we can do actually. So that means for every task we have to reprogram it. So it means that we require a reprogrammable facility in the robot. Then obviously multifunctional manipulators. So I'd already given you the examples that we can perform the painting, we can perform the pick and place, we can use it for the welding and other types. Right? Through variable program motions for the performance of a variety of tasks. So anything, if we consider, it is considered as a robot if it is having a reprogrammable facility. It is a multifunctional device. These are the two important parts. In addition, we have some other requirements. Basically, it should have some sensing. It should have some actuators and a controller also. So by general agreement, a robot is a programmable machine that imitates the actions or appearance of an intelligent creature. So initial robot which has been developed, it was basically developed keeping in mind that whether we can replace our human arm. So if you see the manipulators which has been developed, whether it is a Puma or other manipulators, they have been developed that by keeping in mind that whether we can replace our human arm. So human arm means we have a shoulder joint here, we have a elbow joint, and then we have the wrist. So these 6 degrees of freedom of the human are being captured, and then the human manipulator was developed. Right? Later on, the developments in the robotics field has been made, and then they try to mimic the intelligent creatures. So it may be the hexapod, just like our spider. You might have seen some other robots which are flying. So they have been, drones have been developed and other types of things. So all these are performing some type of actions, and they are appearing just like an intelligent creature. So to qualify as a robot, a machine must be able to sense. So it should be able to get information from its surroundings. As a human being, we have a lot of sensors. Basically, we can see it. Our eyes are there. In case of human, in case of robot, it maybe you can consider that we have the camera. We can hear, so our ears are there. So this means that we can have something which is listening us. So we have the microphones. At present I am using the microphone. My voice is reaching to you. So, and then we have the speaker or headphones through which we can listen what is happening outside, right? So we have the sensor and actuators. Sensor, basically sensing is the hearing, means we are able to listen something. So microphone captures the sound. So similar type of thing is there, right? We have other senses, like we can smell. So nowadays the sensors have been developed which can basically the CO2 gas sensors and other sensors have been developed which can be used for such purposes. We can taste. Taste is still, actually we cannot have the actual sensors being developed, but we can carry out the pH value and we can find out whether it is a acidic or aquatic medium. So that can be done basically. So any robot, because robots have been developed first keeping the human in mind, so all the things are taken from there. So sensing and perception is required. It should be able to sense the environment. And nowadays we are trying to develop the intelligent robots. The focus is towards the intelligent robot. So these sensors are giving us information and we want to intelligently control the environment, right? Then the second requirement is it should be carrying out different tasks, which includes the locomotion or manipulation. That means we are doing something physical. So I'm picking this remote, that is one action, right? I am moving. So when we walk, we are moving. So it is a locomotion. So we are doing something physical. So a robot should be able to carry out some different type of tasks. Right? Reprogramming, I had already discussed this thing. So and then it should be able to function autonomously or interact with the human beings. Today we are talking about the industry 5.0. So industry 5.0, it is focused on the human machine interaction. So there is lot of role to be played in Industry 4.0, where the human and machines means the robot and the human or any machine is working with in collaboration with the human that is being now focus for the research today. So towards the end of my lecture, I will be showing you some examples for this also. Then what are the types of robots? I've just given you some indicative things, but we can have many more types. Basically, we can have the manipulator. You might have heard about the wheel mobile robots, the leg robots, underwater robots, aerial robots, or human-centric robots like assistive, rehabilitation, and other purpose. So we can have the mobile robots. Mobile robots means robots that can move freely in their environment. So they can be either leg mobile robot or wheel mobile robot. We can divide it into two parts, right? Then we can subdivide it into the type of terrains, means whether they are moving inside a indoor room only, or they are moving outside the building or outside, also outdoor robots. Terrain robots, you might have seen that the Mars robot, it is moving in the different type of terrain. So Mars rover has been developed with the different terrains. Terrain means that there is an interaction between the wheel and the soil, and the type of interaction may be different. Maybe the friction conditions are different, or there may be some other conditions which may be different. So we require the different type of handling of the robots. Basically, the power requirement will be changing, or the balancing of the robots will be changing. If I show you again, take you back to this one. This robot, it is moving on the boulders. So when it is moving on the boulders, it should be moving in such a way that the whatever components it is carrying or whatever parts it is carrying, they are not subjected to jerks and other things. Even when we move on in our car or vehicles, we expect that when the rider should not be subjected to jerks, it should be having the comfort. Right? So we have to plan the robot accordingly. So terrain robots are. The second type of robots are the manipulators. So we say that they are the robotic arms. So mostly they are the stationary robots. So there is a base over which these robotic arms are placed. Now we can say that there may be some robots which can be moving also. So suppose I have a wheel mobile robot and I can place an arm over there, and then it can go to certain place and then carry out certain tasks. Particularly when we have the rescue operations, such type of robots may be useful because we have to move to the other place. We have to move in different terrains because there may be boulders, there may be some other type of terrains, there may be. So we have to move it, and then it is carrying the arm. So just like our scavengers, they will be removing the debris, and then they will be trying to identify the persons and other things, right? So we can have a combination of mobile and robotic arm also. Generally, robotic arms are not considered as AI because they do not perform the planning. But nowadays, they are also becoming the AI orientation. Artificial intelligence orientation is coming up because the human and arm machine combinations, there they require artificial intelligence. Otherwise, the person who is working, it may affect the persons being working actually. So nowadays the work is going on to inbuild the AI Sorry for the disturbance. There was some network problem, so I was disconnected. So you can have the autonomous drones. Drones are nowadays used for the various purposes. They are being used for transferring the human organs from one place to another. Because on road, if we are transferring, that will take time. But in air, if we are transferring, that will take less time, and then it can reach to the needy person in time, and the medical doctors, they can perform the surgery and it can be placed at the place, right? So there they are playing. They are being used by the industries for various purposes, for transferring the material from one place to another. And they are being used for the surveillance purposes. Drones are also being used for the agriculture. For example, if we want to find out that which area needs more moisture, or which area is being affected in the large farm, which area is being affected by the some type of insects, we can identify that. Or maybe that because of the bad weather, some area is affected, we can identify such type of. So drones are becoming more and more popular nowadays. Then we have the underwater robots like autonomous submarine. So the submarine, some work is going on, but still it is at the initial stage only. There is lot of skill. The researchers are working how to mimic the fishes, and if it can work underwater, that is being done. There are robots which are autonomous space probes like Mars robot, and then Chandrayaan was sent. It was having a rover which was supposed to land on the moon surface and then do some exploration work. Another direction in which nowadays work is going on is the soft robots. Soft in two senses, basically. Here I had given only the soft computing approaches like fuzzy logic, neural networks, or deep learning, we can say. But in addition, there is another direction of the soft robotics, where we are trying to replace the human hand. Because the human hand, if we see, when we are trying to pick something, we first determine that whether we require a soft touch or we require a hard touch. If I want to pick a cotton, obviously I don't require much pressure. I have to be slightly pick it. Only a small force will be doing the job. But if I have to pick this remote, obviously I have to apply more pressure and then I have to pick. So soft robotics, another direction in which it is going is that they are trying to mimic the skins of the various creatures and then trying to develop the robots. Right? There are robots which learn by mimicking, just like the facial gestures or other type of learning, and they can be used. Another softwares are the software agents. So they are working in the node network, basically. This is another direction. It is not the hardware direction. It is only the software direction, where the bots, means these software agents, they move in the network. They try to determine where is the problem in the network, and for other purposes they are used. Nowadays, we heard about the drug delivery. So, and the diagnosis of the disease. So we can send small robots, maybe nanobots. They will be in the micro size. They will be inserted inside the human body, and then they can take the pictures, or they can clear some problematic area, and they can heal the particular area. So for that also the robots have been developed. They are in the developing stage actually. So these are the various directions in which robots have been developed. Okay. This course, it is focused on the human-centric robots. So human-centric robots means we put the humans in the center of the technological developments and represent a vision of the future where various kinds of intelligent robots will coexist with the human. So we are talking about the era basically which has already been come. So the robots are working or they are existing with the humans. If you might have seen the fiction, science fiction movies, there have been the robots which has been developed. There was a movie Robot in South, it has been there, and then in Hindi it has been dubbed, where the robot has been developed and then it has taken over the human beings basically. Right? So, but the basic principle of the robots, they always focus on basically the 3 rules given by Ashimo basically. So they rules says that the human is given the first priority. If something wrong happens, the robot has to destroy itself, but it should not affect the human beings. Right? So keeping the same principle in mind, basically the human-centric robots have been developed, where robots and the humans are being coexist. So they can serve humans in daily life. They can work in the hazardous environment. So they can include, we can include the home or personal service robots, entertain robots, education robots, medical robots, healthcare and rehabilitation robots, search and rescue robots in these directions. This particular course, because it will be in the assistive robots, basically the Professor Domenico is working in the direction of the assistive robot. He will be discussing more in this direction. So I'm just introducing the term. Assistive robots is a device that can sense, process the sensory information, and perform the actions that benefit people with disability. So they can be used by the person with disability. They can easily walk. They can perform if they have the problem with the arm, basically. So for drinking or for the eating purpose, it can be used basically. Right? If we see the elderly persons, they have the various basically the problems in picking because the muscles becomes weak, so they are not able to pick the things. They are not able to perform their daily routine tasks. So in that case, these assistive robots can help. Right? Then rehabilitation robots, because the persons basically who are having so the persons who are having the problem with the sensory system, or they are having the problem like stroke, they are subjected.
Professor Gupta,
Yeah.
either your network is not like as unstable or mine. I'm not getting your voice in between. May I request all the participants, please tell if you're getting the voice, please write on the chat box if you're correctly able to listen to him. Anyone, please write on the chat box that you're able to. Yes or no, please.
I'd go.
Yes.
Yes.
Voice is audible.
Okay.
Okay. Okay. So in between, there is no break in the voice, right?
Oh.
Then it's all right, perfect. Because in my place, there is some problem I'm facing. So I even connected from my mobile, but still it is creating problem. Okay, please go ahead. Thank you.
Okay, thank you, ma'am. So rehabilitation robots, they have been developed basically to help the persons for therapy purpose, basically. So suppose a person is subject to have the stroke. So these stroke persons, they require the regular exercise. So these rehabilitation therapists, patients to perform the practice movements just by, instead of human trying to support them, robot may support to perform the task. And I already talk about the cobots. Cobot is a collaborative robots which work in collaboration with the human within a shared space. So these are some of the robots being developed in the world, right? So with this brief introduction about the robotics, basically what I am trying to do is I am trying to give you some information, manipulator and mobile robot, small information related to that. Okay. Why I had chosen the manipulator for this is basically that the human arm or these therapist robots, they are being developed based on these robots. Basically, we can have the robots which are having that open chain, so they are serial manipulator, or there may be the parallel manipulators where the robots are, basically various actuators are in parallel to each other. So let us first take the manipulator. This is the Puma 200 robot which has been developed. It is just, I had already told that there is a shoulder joint, there is a elbow joint, and there is a wrist. And what a human being can do, it is just right there in this robot also. This is another robot which is developed for performing a specific task. So in our lab also, we have tried to develop a robot manipulator like this, which is 6 degree of freedom robot. So this is the arm, and then these are the various joints. Okay. So when we talk about the robot, basically, the initial robots, we say that it was based on the manipulator also. So according the robot coordinates have been defined. And the robot classification, now because the mobile and other robots have come, but still these definitions are being told because these are the initial things. So we can have the robots which are performing the operation just like a crane or gantry. So this one is there where all the joints are prismatic joints. Basically, the manipulators, when we talk about, they are either having the prismatic joint or they are having the rotary joints. So prismatic joints means, sorry, here it is wrongly written. These are the prismatic joints. So these 3 joints are the prismatic joints, means I can move along x-axis, I can move along y-axis, and I can move along z-axis. So I will be covering a rectangular area just like the crane will perform its job. Right? So this is basically, this configuration is known as the 3P. Second configuration is cylindrical robot, which is basically having the 2 prismatic joints and 1 revolute joint. So that is shown here. This one is the rotary joint. This is the prismatic joint, and this one is the prismatic. So 2 prismatic. So what basically, so that is why it is been given the cylindrical robot. It is named as the R2P because there are two prismatic and one R joint. Third one is the spherical joint because it covers the spherical shape. It is having one prismatic joints and two rotary joints. So two are. This one is a articulated, or we can say that it is anthropomorphic robot. So it is just a replica of the human arm. All the joints are revolute joints, 3R joint basically. So you can have this movement, you can have this movement and this. So two joints are parallel to each other, another is perpendicular to each other. Right? So this is just the replica of the human arm basically. So that is what is 3R robot, or we say the articulated robots. There was a special type of robot manipulator which has been developed. It is known as the SCARA. It is basically selective compliance assembly robotic arm. So its basic purpose was assemble. So they are having the two parallel joints, rotary joints, and one prismatic joint. It was developed just to pick and place type of thing, or it is performing the assembly task. So when we talk about the robot manipulators, basically, so we have to see the robot reach. Means where I can reach. Right? So whether, for example, suppose I'm sitting at my place and then I'm trying to pick something at a far distance, I cannot pick it. So there are two terms, basically the dexterous space and the reachable space. In the case of manipulator, reachable space is the one where we can reach basically. So by moving different joints, if I can reach to a particular place, that is a reachable space. But it is not necessary that reachable space, when I am reaching, it may be, I can orient it in any direction. So when I am picking this pen and I am moving, I may be moving in this direction, right? Then only I can write something. But if my motions are such that like this, so I cannot rotate it further, or I cannot move it further, that means I am not able to orient it. So we say that dexterous space is one where the robot can reach in any direction. So reach is one of the most important characteristics to be considered in selecting a suitable robot. Because until it is able to reach to a particular point, we cannot perform that particular task. Right? So if we see different type of robots configuration, Cartesian configuration, the reach is a rectangular type space. Cylindrical, it is a hollow cylinder. Is polar or spherical, it is the hollow sphere. And jointed arm configuration does not have a specific shape. So this figure, if you see here, it is the robot workspace. Cartesian workspace, it can reach shape. This is shown as the Cartesian workspace. This is a cylindrical workspace. This is the spherical workspace. And this is some articulated workspace. Right? So when we discuss the manipulator, we discuss the kinematics of the manipulator. So kinematics means, kinematics of the manipulator can be divided into two parts. One is the forward kinematic, another is the inverse kinematics. This is one example of manipulator which is shown here. If I rotate this point, maybe I am rotating it about this vertical axis, then this point will be moving in this space. Right? We know the trigonometric relations, we know the relationships. So we can easily find out that if I move this one angle, it will be moving by this. Basically, r cos theta and r sin theta. That will give me the position of the new basic theta, right? But if we see there is another degree of movement here. So in addition to this robot can move about this axis also. So now it becomes a combination of two angles, theta and phi here. If I have the another one, psi, then I have the third degree of freedom, right? So basically, given these movements of the joints, what will be the final position? If we can calculate, that is given by the forward kinematics. It becomes simple when it is a 2D space, but when we move in the 3D space, it becomes slightly difficult. So there is a technique, DH rules we use, and then we can use it, right? So this is how we can say that if given the joint variables, direct kinematics can help us in identifying the position and orientation of the end effector. There is a reverse of this, inverse kinematics. So inverse kinematics means given the position and orientation of the end effector, because in robotics what we require is that we want to reach to a particular place with particular orientation. So we know the final destination, and then we try to calculate what will be the movements of the different joint, so that we can move the joints by that angle or move motors. I can move and then I can reach to the particular location. So that is the inverse kinematics. So given the position and orientation of the end effector, we perform the inverse kinematics to calculate the joint variables. Right? So just to brief, basically the main forward kinematics, we use the Dana-Witt-Hartenberg conventions. This convention is based on how the joints or two basically joints are or joined together. So suppose I have this one link, this may be the other link, this joint may be in this direction and this joint may be in this direction, this joint may be in this direction. So what is the relationship as I move from this previous joint I-1 to the next joint I? What will be the relationship? Basically, we are moving along this. So 4 parameters are being used for this purpose. They are given as A, alpha, D, and theta. So these 4 parameters, they define the movement, how from one axis to another axis I can move, or how from one link to another link I can move. There are basically 2 conventions for the Dana-Witt-Hartenberg. One is the original Dana-Witt-Hartenberg, and another is the modified Dana-Witt-Hartenberg. So you have to be careful that which one you are using. You cannot mix them together. I am not going into the details of this, how they are being in books, it has been discussed, but I can give you a reference. Basically, you can use the book by Craig. Just if you are following the Craig book on robot motion and control, it uses the modified DH convention. And if you follow the book by Spong, robotics book. Then it follows the original DH convention. So you have to choose one of them only, basically, that is required. Right? So this is one example where DH tools, DH parameters are given. Basically, what we do is we first define the axes for each joint. These are the Z axes being defined. Z axis is defined basically that axis of rotation. For rotary joint, what is the axis of rotation? That is the Z axis. And for prismatic joint, what is the movement direction? That is the Z axis. Then we define, so this is Z0, Z1, you can see here Z2, Z3, Z4, Z5, Z6. Then we define the origins for different points. And once they are defined, we define the x-axis. So Z0 and Z1, it is perpendicular to both, x1 is defined, right? Then Z1 to Z2, as we move, this will be the perpendicular, common perpendicular between the two. That will be the x2 axis. And likewise, you will be defining the x3, x4, and x5, x6. There is no need to consider the y-axis because Dynavit-Hartenberg rule, it does not incorporate the y parameters. So that becomes sometimes problematic actually. So based on the Dynavit-Hartenberg rules, this is the table which has been formed. It contains the 4 parameters theta, alpha, A, and D. Theta and D are defined if it is the conventional one or original DH rule. Theta and D will be defined about the previous axis, I-1 axis, and alpha and A, they are defined about the new x-axis basically. While in the modified conventions, alpha and A are defined about the previous axis, x-axis, and the theta and D are defined along the next Z axis. So this was just a brief of the forward kinematics. Inverse kinematic, we try to identify that what will be the movements, because when we try to move the robot, basically if I'm trying to move that, this robot will be moving from this place to this place. What will be the movement of the different joints? What will be the rotations? So joint variables which can bring the robot the desired configurations, inverse kinematics play. But remember, the inverse kinematics is slightly tricky because it gives you multiple answers. Even if I move, I consider that only one link is moving, you may get 2 values of theta for plus if theta is positive. If theta is negative, you will be having again 2 values for the theta. So with more number of axes, you will be getting the multiple answer, and you have to choose the one which is best fitted. There are technology or techniques available for carrying out the inverse kinematics. I am not discussing that because it requires sufficient time. So then the third thing which comes is the velocity kinematics, because when we move with the manipulators, the rotational speed or the speed of the end effector along different directions will be important. So velocity kinematics is, it gives the relationship between the joint space velocity and task space. So these are the movement of the different axes velocities. Suppose first axis is moving with theta 1 dot, second axis is moving with theta 2 dot angular velocity, and likewise others. So what will be the velocity of the end effector along x-axis, along y-axis, along z-axis, or rotation about x-axis, rotational speed about y-axis, and rotational speed about z-axis. So this is how the Jacobian is defined. Again, I am not going into much details of that, but you get the matrix like this, and that gives you the relationship basically. So that covers the forward kinematics, inverse kinematics, and this velocity kinematics. In addition, we perform the dynamics of the robot, in which we try to identify that what will be the motor capacity, how to determine that the particular motor will be able to sustain the particular load. For example, suppose I am picking again this remote. It is having its weight. Maybe it is 100 gram or 150 gram or 200 gram. So when I pick it, I need to apply certain sufficient force or sufficient torque so that I will be able to pick it. So when we are designing the robot or manipulator, even in the wheel mobile robot also, we have to identify that what type of motor is needed, what will be the torque capacity of that, and accordingly we have to work on that design of the robot. Right? So that is the dynamics of the robot. So this was a brief introduction about the manipulators basically. Now let us move towards the mobile robot, some introduction to the mobile robots also. So mobile robots, you can divide it into two parts. One is the wheel mobile robot, another is the leg mobile robot. These mobile robots, if we compare it with the industrial robots or we say the manipulator, generally the manipulator will be an open kinematic chain and effector. We have the base, and from base to the hand, if I see this is not connected to any other part. So it is an open chain. While a wheel robot, it is a closed multiple chain because it is all the wheels are connected with each other through the grounds. They are in the ground. Right? Similarly, the leg robots also are closed multiple robot chains, because when we stand up as a human beings, our left leg and right legs, they are on the ground. So ground becomes a chain basically which is connecting the left leg and the right leg. But when we are moving, we lift one of the leg. Right? So when we are lifting it, it becomes a open chain. Okay. Meetha, I will just come to your question, just a minute. So that is the, so when we are talking about the leg robot, it is either open kind chain or it may be closed chain depending upon the leg position basically. Right? In case of manipulators, the joints have only 1 degree of freedom. I have a motor, it is moving. So it is a single 1 degree of freedom. But when we are talking about the wheel, we see that wheel, it can rotate up the front and back also. Right? Are you able to hear me? Or is there any voice back?
Yes, sir.
It is fine.
Yes, sir.
There was a small voice break, Vijay, but I mean.
Yeah, I got a message that your network is unstable. That is why I asked.
Yeah.
Okay. So wheels have many degrees of freedom, while the manipulator joints generally have 1 degree of freedom. So control becomes a problem basically. Even in case of this manipulator also, when the degrees of freedom are large, the control becomes a problem. In manipulators, all the joints are actuated with the aim of moving the end effector. while mobile robots may have passive wheels. So we can have the wheels which are moving, and there are some wheels which are not powered. But because of the movement of the other wheels, they are also moving. Even if we see our car or our bikes, only one wheel is powered. Other wheel is a passive wheel. So it moves because other rear wheels are moving. Right? Then the difference is, to control the trajectory of the end effector, we need to control position, speed, and acceleration of each joint. While for the mobile robots, we need to control each degree of freedom of each wheels. So that because we have to control each degree of freedom for each wheel, it becomes slightly difficult. Okay. Now I come to the problem which is in the chat box. Can a design problem be solved based on equation discussed? Right. So even a reference example can be provided, which we can refer to after. Actually, okay. Design problems, obviously you have to solve, but what happens is that these equations, they are becoming more and more complicated. Give me a minute. I will show you the type of equations. Just a minute. It will take some time actually. I have to just search it. Okay, I will show you one example of the equations basically, and you will see that the equations are quite complex. So yeah, Mita, I will share it basically, no problem. But I just wanted to, because you had raised a good question, so I just wanted to share you some typical equations, and then when you will be solving it, it becomes a problem. So we use the numerical methods basically to solve such type of problems. Basically. Right? It becomes more and more complex as the degree of freedom and complexity increases. So that is right. I will come back to this slightly later, or I will share some examples of this. Right? Okay. So now we move forward. I was just discussing the mobile robots. So how the mobile robots have been developed. If we see that how the robots will be, or we see the creatures in the real world, they are moving. So there is a movement due to rotation. Wheels are the examples of that. So we can have the wheel mobile robots. There may be a conveyor belt. So tracked wheels mobile robots, they have been developed where this, when particularly the terrain is quite difficult, in that case, this tracked wheel are more better. Even if you go into the hilly areas during the snowfall, basically, they use the tracked wheel base, right? And our armies anyway, they are using this tracked wheel. So convey is there. We can walk, we can swim. So same thing has been tried to replicate in the robots. Fly, reach to a particular place, bend. Snake type of robots can they will be bending and then crawling, bending action, poking, rolling, right? So we can use the legs. They can be used for walking, crawling purpose, climbing, jumping, and hopping purpose. Wheels being used for the rolling purpose. We can use the arms for swinging purpose. We can use them for the crawling purpose and climbing purpose. This is one example. Arms are being used for moving, basically, right? Then flippers can be used for the swimming purpose. And there are many other biological examples, right? And these becomes the effector. So leg is one effector. If we see the leg, it is just a manipulator. If we invert the manipulator, it is a leg, right? Wheels, so we use the motors. Arms is again just legs or arms, they are similar type, basically. Flippers, we require an action by like this so that the swimming action becomes easily. It can be this movement or it can be a combination, different combinations are being. So by analyzing the movement of the creatures in the world, they have been designed by the various researchers, right? So if we talk about the leg robot, basically, so we can say that we have the locomotion. The basic purpose of the locomotion is to move the robot around. So the robot is performing two tasks. One, it is moving around, and then it is performing some other tasks. So to move other objects around, that is the manipulations. So wheel mobile robot, we are just considering locomotion, and manipulators we had already discussed, basically, right? So this I had already covered. While most animals use legs to get around, leg locomotion is a very difficult robotic problem as compared to the wheel locomotions. The main problem comes is the balancing. Even if we see that human beings, we can able to easily stand still. We can walk or we can just stay at a place. But if you see that when we are standing at a place, after some time we have to change our posture, right? Because we try to get instability. So we have to change the posture, and again we stand. Basically, we keep on standing, basically. But our posture will be continuously changing. So in robots also, it is being needed that they should be stable. So it is like that, right? So type of locomotion in nature is these locomotions, and the kinematics of the motion which has been explored by the researchers is like this. And these basic mechanics principles have been used by the researchers to design the robots like this. So if it is the crawling, just like the inchworm, we can create the longitudinal vibrations type in the robot, and then it can move. For sliding, we require the transverse vibrations and like that, right? So I had already discussed that for locomotion, any robot needs to be stable. We talk about the two types of stability. One is the static stability, means it is just stand still without falling over. In dynamics, it is moving. And if you see, actually, when you might have started riding the bicycle, the stability, static stability, it is difficult as compared to dynamic stability. Right? So, right? So for static stability, we require more number of legs, enough legs or wheels on the robot to provide the sufficient static point of support. So when we are talking about the mobile robots or leg robot, basically we say that what is the point of support, right? As a human being, when we are stand still at a particular place, we have our legs. So if I draw them, I have this leg, this foot on the ground, this foot on the ground, and then on this, between this, so they become the point of support. All the points in this space and in this space, they are on point of the supports, right? So this total figure, if I draw, this is the point of support for the human being, basically, right? But when I lift one of the leg, so suppose this leg is lifted, so now my point of support becomes only this, right? So this point of support is required because we try to give a posture to our body or whatever robot is there, its posture is given such that the CG, center of gravity, should be always lying in this point of support. Or we say that instead of point of support, because there are number of points on this support, so we say that it is the polygon of support. It is better to call it as the polygon of support. So our CG should, for the static stability, our CG should be always on the polygon of support. That is the basic requirement. Obviously, when we are having the more number of legs, static stability becomes quite simple. I had already discussed this. Center of gravity must fall within polygon of support. So we require, basically it is considered that at least 3 legs are considered to be more stable because they make a tripod. Tripod is always stable as compared to the bistable condition, basically 2 legs on the ground. Okay. So we require a minimum of 2 degrees of freedom to move a leg forward. We have to lift and we have to perform a swinging operation. 3 degrees of freedom are required for each leg in most of the cases. And if we can have the 4th degree of freedom for the ankle support, it may improve the walking. But with 4 degrees of freedom, we are increasing the complexity of the design. And each leg can be considered as a manipulator. So this is about the leg. So this is one of the example of the leg support. You can see that it is just like a manipulator. Once, so we have the abduction, adduction, and guide wave. Right? Coming to the wheel mobile robot, we normally see them. So wheel assembly is required. Most robots use wheel for locomotion because of the simplicity of the control and stability. Right? But if we see, the animal does not have wheels. Only some animals have the wheels, but others are having the legs. Because nature has given the animals stable perform, they can balance their body. So that intelligence is already built in the animals. And once it is the leg robot, obviously we can overcome number of obstacles. So if we see from obstacle avoidance and other purpose, leg robots are most considered to be more better as compared to wheel mobile robot. But if we require the speed, wheel mobile robots will be having more speed as compared to the leg mobile robot. So most robots have 3 to 4 wheels. 3 wheels are sufficient to guarantee the stability. With more than 3 wheels, a flexible suspension is needed. So it depends upon the type of applications. So there are 4 basic types of wheels. Standard wheels we normally use. So there is a hinge here, and then it is wheels. Right? Caster wheels, which we use in the our chairs. So there, the third wheel is automatically aligned. Right? It is just given this type of shape, so it is mostly aligned. Right? Then we have the Swedish wheel, which is having 3 degrees. Can rotate about their own axis. They can around the rollers, they can rotate, and then around the contact point they can move. We say that they are the omnidirectional wheels like this. Right? Swedish wheel with 45 degree, it is now known as the omnidirectional wheel. And you can have the, instead of this wheel like this, you can have a roller here, then that becomes the ball or spherical wheels. The biggest advantage with the omnidirectional or Swedish wheel is that I can move this vehicle along the left direction, right direction, or I can move it front or back directions without any movement in the other directions. So that advantage we are having with this. Right? So basically, we have to have a trade-off between the stability, maneuverability, and controllability. Maneuverability means how many degrees of freedom a robot can manipulate at a time. Controllability means how many degrees we can control. Right? For example, suppose this mobile robot, if we consider this car, it is having 3 degrees of freedom. It can move along front direction, it can move sideways, or it can steer. Right? But out of these 3, I can control only 2. One is the movement of these wheels, another is the steering. Right? So it is having 3 degrees of freedom, but we can use only 2. So that means some motion cannot be done. Means sideways motion cannot be done. What we do is that suppose I require this sideways motion, I have to take the car front and back number of times, and then I can place it on the side. The 2 available degree of freedom can get to any position and orientation in 2D. So when we talk about the wheel mobile robot, holonomicity is required. Holonomicity means it is based on the holonomic, whether the robot is holonomic or non-holonomic. If the number of controllable degree of freedom is equal to the number of degrees of freedom of the robot, it is holonomic robot. But if number of degree of controllable degree of freedoms are less than the number of degree of the freedom of the robot, it is non-holonomic robot. And if the number of controllable degree of freedom is larger than the number of degree of freedom of the robot, it is a redundant robot. So a car is non-holonomic robot, a human arm with more degree of freedom means 7 degree of freedom, it is a redundant system, right? So I can skip this. Another term which is generally used in the wheel mobile robot is the maneuverability. It is basically the combination of the mobility available based on the sliding constraints and additional freedom contributed by the steering. So basically, we can say that degree of mobility is the delta m, small m, remember here. Degree of steerability is suppose delta s. Then degree of robot maneuverability is the delta capital M, that is equal to degree of mobility and degree of steerability. Right? So if we have the tripod type of robots, the degree of maneuverability will be 3. It does not have any steering, but all the 3 wheels can be mobile, each degree, right? Like this. Tricycle, you might have used the tricycles. So the maneuverability is 2, and it is the mobility is 1, and steerability is 1. These we by pedal, when we push pedal, these wheels will be moving. So that is 1 degree of freedom for these wheels. And then by steering, we are steering this front wheel. So that is giving me 1 degree of freedom here, and total becomes a 2 degree of maneuverability for the tricycle. Okay. I'm always inspired by this Boston Dynamics actually. So I wanted to show you some video. Let me just play the video. I have the, I think 10 minutes time. So just. So Boston Dynamics,
a pioneering robotics company helping to lead in a technological revolution or a sign of the coming robot apocalypse. Over the last decade, Boston Dynamics has built some of the
you can see this robot, it can move just like a human being on various type of terrains.
most impressive robots in the world that can run, jump, and even dance better than some of us humans. Boston Dynamics robots. Boston Dynamics was created was the Big Dog in 2005. The robot was designed to be able to carry heavy gear for soldiers in terrains too rough for vehicles. Instead of wheels, it had 4 legs, allowing it to move across surfaces that would defeat wheels. Big Dog was 3 feet long and stood 2.5 feet tall, making it about the size of a small mule.
So they tried to develop the
awkward and early videos posted by
Big
Boston
Dog
Dynamics
first.
YouTube channel. The robot was surprisingly proficient at keeping its legs under itself. Even when it was kicked by its tester, the Big Dog did not fall. Combat. In 2010, Big Dog was improved. It could run at 5 miles per hour and accurately reproduce the 2 drunken men carrying a soap. Little Dog, which just looks like a legged Wi-Fi router. Big Dog Olay, which hopefully one day can replace the tortured Bowles and Spain. The Christmas versions of Big Dog are putting reindeer out of their jobs. Plot twist. The woman is a robot. In 2012, the latest generation known as the Leg Squad Support System, or LS3, was developed. It was a significant upgrade compared to Big Dog and could operate in hot, cold, wet, and dirty environments. It could also run faster at 7 miles per hour and was roughly 10 times quieter. Despite improving Big Dog and investing millions at the end of 2015, the Big Dog project was discontinued. It showed the world how robots could take over the world by throwing bricks at humans.
Reinvent your hiring with Test Gorilla. We offer you seriously smart screening tests crafted by experts. We save you time.
In 2009, Boston Dynamics started working on a human-like robot named Petman. The robot can walk at 3.2 miles per hour. An upgrade and could, besides walking, also developed for the U.S. Army, who planned to use the robot to temperature and sweats. Sandflea is another robot developed for the U.S. Army, and it has no trouble jumping over a 2-story building. The piston is powered by CO2 and can make 30 jumps in a row before running out of power. Sandflea was designed as handy surveillance in places that would otherwise be inaccessible or too dangerous for humans. The tricky part of the process was keeping Sandflea oriented as steadily as possible during the jump, since it was also intended to record videos while in midair. The navigational system is so specific that soldiers can even direct the Sandflea to jump 2 stories in an open window. Fun fact, Sandflea was used somewhere else. We know Boston Dynamics had their eye on 50 miles per hour for a bit, and the top speed of a biological cheetah, around 70 miles per hour, may ultimately be within reach. We're not sure when this will be, still considering that cheetah began from the top speed of 18 miles per hour and came to 28 miles per hour in less than 5 months.
You can see
How long
that
will we
they
have to get
were
comfortable with the possibility of being chased down and
trying to
by a
achieve the cheetah
robotic
speed, and then
Fun fact,
they
Boston Dynamics cheetah speed record at 28.3 miles per hour was incidentally faster than Olympic champion Usain Bolt, who got the world record for the 100-meter. Wildcat was a 4-legged robot developed in 20. Stood 6 feet 2 inches tall and weighed 330 pounds. The company
then they
initially made
developed
the
the
robot to be a
Atlas.
DARPA robot height of about 5 feet tall. The new version of Atlas is designed to operate debut. In 2016, Atlas received a new design with a height of about 5 feet tall. The new version of Atlas is designed to operate both outdoors and inside buildings. It uses sensors in its body and legs to balance and LiDAR and stereo sensors in its head to avoid obstacles. Sadly, Atlas was heavily bullied and cyberbullying was taken to a whole other level. In 2017, Atlas was improved even further so that it could
was
jump,
able to
but
jump
far
also.
more impressively, it could do a backflip. With the next generation in 2018, Atlas could run outdoors. Now he could finally escape from the physical abuse in the lab. I hope he's fine. During the development process, new techniques were developed, allowing Atlas to use its whole body, complex algorithms to do parkour.
At a practical level, it's a platform for us to do R&D on.
So pushing the limits on weighing in at around 160 pounds. It was faster. Seen on Spot today. One of the quietest robots that was also heavily.
they developed number of such robots.
The 3D map together. Spot robots might. To celebrate the new ownership, they launched a like picking up boxes and placing them somewhere
And
else.
this is another robot, basically. You can see
6.17 with a group of. In 2017,
Fender was
Fender
introduced,
which the company has declared as, quote, a research venture into wheeled robots. The wheeled robot stands 6.5 feet tall and can reach a top speed of 9 miles per hour.
So it was a combination of
Designed for
leg and
logistics
the wheel.
tasks like picking up boxes and places to depalletize fast and accurately. The second is Stretch. Stretch is a versatile mobile robot that can unload trucks and build pallets. These robots can work autonomously. Meanwhile, warehouse workers watching this are getting stressed. It is unbelievable how far Boston Dynamics has.
So I stop at this point, and then I wanted to show you another video, basically. So this is the robot being developed by the IIT Bombay, actually. It is a 6-leg robot, and you can see the structure, very heavy structure it has been built. It can walk. So it is a hexapod configuration, and then you can see that 3 legs will be always on the ground to make it stable. This is the one. Then which is shown here is 1/3 of the maximum speed. Then it was taking a turn. So then when it is taking the turn, it is rearranging the legs. It is moving up and down. It can perform that type of task, just like push-up. Can rearrange the legs and then move towards the that time, whatever was the electronics available, that was done, and then servo drive based. So this was about the some videos I wanted to show. Let me go. Underwater, some robots, some example. This is the underwater. Oh, this is the aerial, and this one is the underwater robot. Unmanned aerial vehicles or unmanned autonomous underwater vehicles, which has been developed. Human fingers are being replicated for grasping purpose. So grasping is another direction. Professor Domenico will be discussing more about this. And then as I told you that initially, that the industry 5.0, the focus is the interaction between the human and machine. So this is example BMW collaborative robot, where the machine, this robot is performing some task on this engine. So engine is being picked up, and then this human is trying to perform the task with the help of this robot. So human and machine both are interacting, and they are performing the task. This is another example. This is one assembly process which is done. So some parts are picked and kept by the robot, and some parts are picked and kept by the human being. Right? And then these workers, they are wearing some exoskeleton devices to perform the powerful task, basically, that human beings cannot do, but these machines can perform that task. There are many more examples, but I'll just try to summarize. So at IIIT DMJ, we are working in the direction of ANN and machine learning based robots. A manipulator, I had already shown you. The multi-terrain robots also I had shown you. So it has been developed. These are some example of the grasping. So different objects can be grasped, even very soft or very brittle materials or hard materials, they were able to. So this was based on the ANN and fuzzy controller based. Okay. Then the mobile robot direction, persuasive vision. brain controlled mobile robots, character animation using corridor wave methods. These are the directions the research is going on. And now we are moving towards the assistive and rehabilitation robotics. So some task is already going on. Right? Thanks for the patience in hearing, listening. Any questions you have, you can ask me.
Thank you, Professor Gupta, for your very nice introduction. And I hope if people have any questions, please feel free in asking. Else, we will have a small break of 8 to 9 minutes, and then we will be resuming.
I think there is no questions. So thank you for listening, and we will be meeting at 3:40.
3:40. We'll be meeting at 3:40 for 1.5 hours.
We'll break for 10 minutes and then.
So we can put this live off again. Yeah.